So, our next problem is going to fully develop the system of modular arithmetic for us in a nice sort of linear way where we have four integers a1, a2, b1, b2, and we have that a1 is congruent to a2 mod m and b1 is congruent to b2 mod m. And we can see step by step how this process is going to unfold. Part A wants us to show that if we take A1 and add it with two different values that are still congruent under mod m, that the sum of those will be congruent as well. Part B asks us to take the same value for B2 and add two different values to those ones, but those two values are congruent mod m, and show that that sum is congruent mod m. And then finally, part C is going to ask us to just take the two sets we have, that the fact that A1 is congruent to A2 and that B1 is congruent to B2, both mod m, and no matter what values they are, it will preserve the congruence when we add them together. So let's establish the facts that we know. We know that from here we can establish that a1 minus a1 minus a2 over m is equal to some integer k. And from here we can establish that b1 minus b2 over m is equal to some integer j. And we can use these two pieces of information to hopefully get what we want. So, let's start, obviously with part A. If I want part A to be true, I have to come up with that fraction where we can determine if it's equal to an integer when divided with m. Now, it's a little different from how we did it last time, but a lot of the process is the same. So let's note the fact that, for instance, we have in part A b1 and b2 in our equivalent statement. So the a1 is the same on both sides, but the fact that we have b1 is congruent to b2 on the two different b values, that maybe hints that I want to start out with that guy right there, because I can establish that b1 minus b2 over m, I know that this is an integer. We know that that's equal to j. But from here, I already have two of the building blocks that I need, the b1 and the b2, with an established congruence. Now I just need to fit a1 in there somewhere. Now this takes a little bit of algebraic maturity to understand what we must do. So what I'm going to do is, without changing the value of the fraction, without adding really any value at all, I am going to add a1 to the b1, to the numerator in general. But I'm also, since I added an a1 to the numerator, I'm also going to subtract a1 as well, minus b2. over m. That way, I've technically, all I've done, I've added 0 to the numerator, because a1 minus a1 is just 0. And I have this positive a1 minus an a1, that's a 0. I've technically not added any value to the numerator at all. But what this can clearly show me is that if I have basically everything I could want right now. A1 and B1. Oh, whoops, wrong thing. A1 and B1 I have grouped together. So I'm just going to write that in parentheses. A1 plus B1. Then I have negative A1 minus B2. Now I can factor out the negative from both of them and get a minus A1 plus B2 over M. And now I have everything I need to complete part A. We have that A1 plus B1. When we see the difference between that and A1 plus B2 is an integer j. So we have established the fact that j is the same, j the integer is the same as A1 plus B1 minus A1 plus B2 all over M. And since the difference of those two terms when divided with M is an integer, that establishes the fact that A1 plus B1 is congruent with A1 plus B2 mod M. Oh. We have now proven that fact algebraically. So we're going to use a similar technique for the next one, for part B, which had asked us to find, let's see, what was it? A1, A2, and B2 on both sides. So A1, well, I'm going to start out, since, like, using the same logic I did in part A, since I have my A1 and my A2, and the B2s are the same, I'm going to start out with the fact that A1 minus A2 over M is K. So A1 minus A2 over M is equal to this integer K. And you probably can see where I'm going with this. I'm going to take my fraction and in the numerator add a B2. B2. Then I have a minus A2. And then to make sure I haven't added any value in the numerator, I want to subtract the B2. So the B2s would cancel out and become 0. Therefore, we haven't changed what this fraction is equal to in any way. And then, of course, what we will do is our factorization, like we did last time. A1 plus B2 plus B2 minus A2 plus B2 over M is equal to K, an integer. So we have established that K is the same as A1 plus B2 minus A2 plus B2 over M, which implies, because of that definition of congruence that we have, that A1 plus B2 is congruent to A2 plus B2 mod M. And we have solved for part B. Now, the final part, part C, A1 plus B1 congruent to A2 plus B2. So, a little bit trickier. A1 plus B1 is congruent to A2 plus B2. How can we sort of resolve what's going on there? Well, we have two important facts. We have already established that A1 plus B1 is congruent to A1 plus B2 mod M. And we have established that A1 plus B2 is congruent with A2 plus B2 mod M. Interesting. Now, we have, maybe you can see what we're going to do here, but like we had done in the previous video, we have established something called the transitive property. And if you can remember, that says, I'm going to use different lettering than I used originally, but if x is congruent to y mod M, and if y is congruent to z mod M, then x is congruent to z mod M. That transitive property that we established previously is now going to come into play. So, if you're trying to compare like these two formula out, we have that A1 plus B1 would kind of be like our x value, and A1 plus B2 is our y. But we also have that A1 plus B2 is a y over here, and that's congruent with some new value z over here. And putting the formula to work, we know that x must be congruent to z. So we can use the logic we have previously established to put together that A1 plus B1, since that is congruent to A1 plus B2, and we know that is congruent to A2 plus B2 mod M, then all three of these equivalences hold. But importantly, we get the simplified result we want, so where A1 plus B1 is congruent to A2 plus B2 mod M. So this establishes that no matter what module system we're working with, if A1 is congruent with A2 and B1 is congruent with B2 in that same module system, that the sum of those values will also be congruent. So we have that, again, A1 is congruent to A2, B1 congruent to B2. Add up the left side, add up the right side, the congruence will hold. So this can make things much easier when trying to find congruences. So if we can remember, back when we did residues, we know that, like for instance, like 137 mod 10 is congruent to 7 mod 10. And 592 mod 10 is congruent to 2 mod 10. And using that idea, we can simplify a process like this, where if I wanted to find out what those two were, mod 10, I wouldn't actually have to add 137 and 592 together. I would just add 7 and 2 together, because they are equivalent. And 7 and 2 is 9, so we get that this is just 9 mod 10. And from that fact, we know that if we did add them together, we would also generate the fact that 729 mod 10 is also equal to 9 mod 10. As a direct result of what's going on there. So we can use this, these addition properties to come up with very powerful ways to solve problems in modular arithmetic.